We now look at chapter 25, which is capacitors. So a capacitor is any device that can store charge. So anything that can store charge becomes a capacitor. Now, if we just have a simple sphere on a stand, then we can give it some charge by induction or conduction, and that charge will stay there, so it becomes a capacitor. But this is not a very good capacitor because it will lose the charge to the atmosphere. And what we find is that if we have another charge which is negative, and we keep these two close together, then the charge on both of them stays for a longer time. Now this would become a capacitor, but not a very nice one. Better capacitors are if we have, for example, two parallel plates, and one of them has a positive charge and the other has a negative charge, and the two plates are close together, then the distance between them is d, and they have some area, then they can store more charge. So that's how we usually make these what we call the parallel plate capacitor. Now, a capacitor is a electronic component in almost all electronics. And it is used in, for example, in the camera flash, where it takes a flash. The reason why we use this is because it can store charge slowly, but it can give up all the charge very, very quickly to create a flash of light. It's also used in radio sets, and it's used in electronic filters, which are devices to separate different frequencies, and in many other electronic devices. Now let's see how much charge a capacitor can store. So let's suppose we take a parallel plate capacitor. So we take a plate and we take another plate which is parallel to the first one. They are separated by a distance d, and the area of this plate is A1, the area of this plate is A2. And if we attach a potential difference across these, so right now there's no potential here, there's no charge on it. Once we connect the switch, the electrons will start moving this way. They'll start collecting on this plate, and as they collect here, the electrons on this plate will be pushed away, and the electrons will be moved away from here, and they will go into the battery, and so we will have a net positive charge here. Whatever is the negative charge here will be exactly the same as the positive charge on this other plate. Now, as the charge keeps on collecting, the potential difference here keeps on increasing, because, and due to that, the new electrons will try to prevent electrons from here coming in, and once this charge reaches a certain value, the potential difference across the two plates becomes the same as the battery potential, then no new electrons can come in, and at that point we say the capacitor is fully charged. So this Q will keep on increasing until it reaches Q, or we can call it Q max, and Q max is the maximum amount of charge that can be stored on a capacitor. So we will have negative Q max on this side, positive Q max on this side. As a whole, the capacitor has no charge. It has equal positive and negative charges, but we say that the capacitor is charged to a charge of Q max. Now we'll see what this Q max depends on. So as we can see or imagine that if the potential or the battery is bigger, it has more EMF, so it can force more electrons onto here. So the charge Q max, which we'll just write as a Q, will be proportional to the potential difference of the battery. And we can say that this Q is equal to a constant times the delta V. That constant is the capacitance of this capacitor. And this capacitance will depend on some factors. It will depend on the distance, it will depend on the area, and it will depend on what's in between the two plates. Now, the units of capacitance will be, if we rearrange this equation, C equals Q over delta V. The charge is coulombs, and the delta V is a volt. And this coulomb over volt is called a farad, written with a capital F. And the farad is the unit of capacitance. Now, let's see what the capacitance will depend on. We say it depends on the area and the distance, but let's evaluate that, and we'll see that the charge is equal to C delta V. So the capacitance is Q over delta V. Now, if we have a plate, let's look at this plate edge on, and if we recall that we had a in a previous chapter we had made a cylinder like this, and we had the electric field coming out was given by sigma over 2 epsilon naught, where epsilon naught is the permittivity of a free space, and it's equal to 8.854. It keeps on going, 10 to the power minus 12, and it's coulomb square over Newton meter square. Now, we have another plate over here. These are two parallel plates. So the other plate also has the same thing, and it has an electric field of the same value. And so the electric field in between these is twice of each of these. So the electric field in between the plates becomes sigma over epsilon naught, where sigma is the charge density, and that is the charge per unit area of this plate. So it's Q over A over epsilon naught. Now, from this equation we can see that the charge on each plate is going to be E epsilon naught times A, and we can substitute this charge in here. So we'll plug that in here, and so our C becomes E epsilon naught A over delta V. Now we know for a parallel plate the electric field between the plates E, the distance is D, and the potential difference across them is delta V. Then we know that delta V equals ED, and so we can replace this delta V with ED. The E's will cancel, and this becomes sigma naught A over D, and that is the value of the capacitance of this capacitor. So if the area of the plate is A, this distance between the plates is D, then that is the value of the capacitance. Now let's do a small example on this. So let's say we have a parallel plate capacitor, and the area of one plate, let's call that A1. This area is, let's say, A2. So let's say A1 is 10 centimeters square, and A2 is also 10 centimeters square. Then the area that we use for finding the capacitance is just A as 10 centimeters square. We do not add the two together. Let's say that the distance between the two plates is 1 millimeter. So now we plug these in. So the capacitance becomes epsilon naught, which is 8.854 into 10 to the power minus 12. That's Coulomb square over Newton meter square. And then the area, which is 10 centimeters square, which we convert into meters. So it's 10 to the power minus 4 meters square over centimeter square. That becomes the area. I divide by the distance between them, which is 1 millimeter, and we multiply with 10 to the minus 3 meter per millimeter. And now we can cancel out the millimeter with the millimeter, and the centimeter square with the centimeter square, the meter square with the meter square, and we get capacitance comes out to 8.854, and we have, oh, there's a 10 here, into 10 to the power minus 12, and the units become farad. So that is the capacitance.